Hi, I'm Andrew, and my group, consisting of myself, Babs, and Chris, present to you our project on cables and cords. Our goal with this project was to test various types of cords to see which would work the best as a bungee cable. We decided to test three different types of cables that could be commonly found in an everyday household. These are a bungee cord, an HDMI cable, and some paracord. Each of these stretches a different amount, which means they all have different spring constant values. This is because they all vary greatly in elasticity. To determine which worked the best, we tied weights to the cables and dropped them from a high place. These weights weighed 5 and 15 pounds. We then measured how much energy was retained in the cord. We could determine this by measuring how high the object bounced back up. This tells us how much energy has left the system. The more energy that leaves the system, the more energy that is put into the object. If that object were, say, a person, then if too much energy were imparted into the object, they could receive some damage. Also, if the cable lacks elasticity, the cable could snap.
That broke. Oh, it broke the cord!
Understanding how to test cables of varying properties can improve the safety of bungee jumps. Now, let's talk about our trials. To start, we will be going over the bungee cable. Our bungee cable has a resting length of 89 centimeters. We decided to use this length for the paracord and HDMI cable as well. After using Logger Pro to estimate some distances, we were able to calculate the percentage of energy that was retained as a spring force in the bungee cable. The weight bounced back up to about 65% of the distance it fell each time. We also decided to calculate the spring constant for the bungee cable. This was found to be about 88.9 newtons per meter. We expect the same results should occur after rerunning the bungee trial with the 15-pound weight.
3, 2. Well, that's pretty good.
We found that with the heavier weight, the amount of energy retained was about 72%. This was greater than expected. We believe this could have been caused by us stretching out the bungee cable over multiple trials. We then ran the same calculations as before to find the spring constant again. This time we found it to be a bit less at 73.2 Newton meters. This decrease could also be explained by the bungee being stretched out.
Now let's move on to our paracord trials. Using the 5-pound weight with the paracord showed that only 32% of the system's energy was retained with each bounce. The spring constant was found to be 202.2 newtons per meter. We also ran a trial using the 15-pound weight.
Okay.
The paracord was able to once again retain 32% of the system's energy using the 15-pound weight. After calculating the spring constant again, we found it to be 222.1 newtons per meter. There is one final cable that we decided to test. This is an HDMI cable. Once again, we will be starting with the 5-pound weight. When using the 5-pound weight, we saw that the system retained practically none of its initial energy. The weight didn't bounce back up at all. We calculated the spring constant to be 2,222.4.6 newtons per meter. Finally, it's time to run a final test using the HDMI cable and the 15-pound weight.
Okay, ready? Guys, ready? That broke. Oh, it broke the cord!
Our HDMI cable was unable to withstand the weight and snapped. You may have noticed earlier that our graphs for vertical position show a pretty clear pattern, especially if you look at our trials for the bungee cable. The graphs create waves. There's some information we can glean using the observation. First, the height of each wave decreases by the same ratio each time. For example, in our trial using the bungee cable and the 15-pound weight, we found the height of the wave decreased by about 28% between each one. This tells us that the cable can retain about 72% of the energy each time the weight bounces. We also noticed that using a higher mass leads to a lower frequency, meaning that the heavier the weight we used, the fewer times it would bounce over an interval. Another cool observation we made was that the wavelength stayed about the same for the entirety of the graph. So, why do we care about this? Well, how can this information help us in the real world? Bungee jumping is a popular and dangerous activity. This project showed us that the cable with too high a spring constant can lead to catastrophe. We also realized that too low a spring constant can be bad. Other than the cable itself, the object's mass must also be taken into consideration. The information we learned in this project holds many applications outside of bungee jumping. For example, engineers need to consider spring constants and mass when designing things like elevator cables, climbing ropes, and securing loads. In the end, our tests showed that you need to carefully consider the properties of your cord before you use it for any activity.
Okay, ready? Guys, ready? Go. Yeah, bro. Oh,